Welcome to Facts for Real Videos. This is the second tallest structure in the world, the Merdeka Tower. However, did you realize that beneath the water are equally enormous structures? Submarine railway tunnels and oil platforms the size of skyscrapers are among the most ambitious construction projects in history, as are megaprojects under the sea. We'll reveal the absurd scale of these projects today and go over how they were constructed. Let's examine the 500-meter-tall Bullwinkle oil platform, which was moved to the ocean's middle, and how Bangladesh's Padma Bridge overcame the difficulties posed by a surging river thanks to steel piles bigger than skyscrapers. Let us begin by discussing the absurd dimensions of oil rigs. Every day, almost 100 million barrels of oil are used worldwide. This implies that in order to keep up with the growing demand, oil corporations are always searching for new oil reservoirs. Large offshore drilling platforms are being constructed in order to access the more than two-thirds of oil and gas that are stored beneath the ocean floor. The earliest offshore platforms were constructed around the close of the 1800s and drilled in regions with sea depths of less than 100 meters. Since then, oil firms have made significant technological investments, and as a result, oil rigs have grown to heights that are on par with some of the highest skyscrapers on land. Shell finished building the first really large oil rig in the Gulf of Mexico back in 1977. Built at a cost of $100 million, the Prospect Cognac platform stood taller than the Empire State Building. Taller platforms have become more popular since Prospect Cognac, and as of right now, there are 4 oil platforms that are higher than 500 meters. The Bullwinkle platform by Shell, which was put in place in 1988, is the oldest of these. It is nearly as tall as One World Trade Center in New York, standing at 529 meters. Chevron constructed the 640-meter-tall Petronas-compliant tower at the turn of the century, which continues to maintain the record. It was the highest building in the world at the time, but it has since been eclipsed by the Burj Khalifa in Dubai and, more recently, the 679-meter-tall Merdeka Tower in Malaysia. It doesn't end there, though. Today, floating oil platforms can be found up to 2,900 meters below the surface of the ocean. However, how are these enormous platforms constructed underwater? When an oil rig is finished being built, it is transported to the middle of the ocean from fabrication yards on land. For instance, Bullwinkle was constructed in Texas while lying on its side to create its 400-meter-long base or jacket. The massive structure was carried onto a barge that was constructed parallel to the jacket in order to be transported to its final location. It required 5 days to safely load the platform onto the barge, requiring the diversion of traffic on the Gulf Intracoastal Waterway. Furthermore, it took 3 days to get to its objective, which was directly above an oil well. At the time, it was the biggest building ever transported. Bullwinkle was tipped 2.5 degrees to submerge in the water once it was directly above the oil well. Afterwards, the engineers used underwater cameras and remote controls to secure the platform to the ocean floor. The deck for Bullwinkle was made independently in Louisiana and fastened over the jacket. The project was completed in more than 5 years and at a cost of more than $500 million. Since then, only one other offshore platform has been able to top the record for being the largest structure ever moved. Off the west coast of Norway, it was the transportation of the 460-meter-tall Troll A platform. The majority of oil rigs, like Bullwinkle, are static and are used to drill up to 500 meters into the ocean floor. Bullwinkle is still the tallest offshore fixed platform. But gas and oil are also present further deeper in the ocean. Compliance towers are an option for engineers working at depths of 500 to 1,000 meters. Compliant towers are tall, narrow constructions made of steel and concrete that can sway with the waves and withstand greater forces. On the other hand, 3 kilometers below the surface of the ocean lie the world's lowest oil wells. It is not feasible to construct steel structures at these depths and attach them to the ocean floor. Drilling is therefore made possible by engineers using floating oil rigs. These oil rigs are precisely positioned over oil wells by means of sophisticated positioning systems, and they are linked to the deep wells by means of kilometers-long cables and anchors. BP, Chevron, and Shell jointly run Perdido, one such oil rig. Through a 170-meter spar, a long floating cylinder that is buried in the ocean and secured to the seabed with 9 mooring lines, Perdido allows drilling at a depth of more than 2.5 kilometers. When Perdido, which was built in Finland in 2008, was revealed 8 years later, it was the world's deepest oil rig. Stones can operate 2.9 kilometers below the ocean's surface, which allows it to retrieve oil from deposits as deep as 8,000 meters. Large oil platforms are not the only undersea megaprojects of crazy proportions. The construction of kilometer-long underwater tunnels is extremely difficult. In the early 1800s, there were attempts to build the first underwater tunnel in history. The tunnel began to flood, and although they attempted to utilize the same methods as in mines at the time, they were unable. Yet with the aid of modern technology, what was formerly considered unattainable might become a reality in the ensuing decades. With the use of the recently developed tunneling shield, the 400-meter Thames tunnel might be completed in 1843. Subsea tunnel technology has advanced significantly since then, and the development of the tunnel boring machine allowed for the realization of considerably larger-scale projects. The 50-kilometer Channel Tunnel that connects Britain and France currently has the longest underwater section in the entire globe. It is regarded as one of the most incredible engineering achievements of the 20th century and was finished in 1994. Long before the tunnel was actually built, plans were being considered for a means of crossing the English Channel. Due to inclement weather and rough seas, traveling across the channel by boat has always been an unpleasant experience. Thus, as soon as technology progressed enough, the United Kingdom and France began work on drilling a tunnel under the sea. The lower chalk layer, composed of chalk marl, was determined to be the easiest to drill through by scientists who studied the geology of the English Channel's bottom before beginning construction. 11 enormous tunnel boring machines were used when the excavation began in 1987. Each device weighted more than 70 passenger buses and measured over 2 football fields in length. 6 from the UK and 5 from France began digging. They used conveyor belts to move the rubble after cutting through the chalk. In order to assist the tunnel endure the tremendous pressure exerted by the waves, concrete reinforcement was added to its sides during the excavation phase. 4 years later, in May 1991, the French and English sides of the tunnel finally came together. 3 parallel tunnels make up the entire project. 2 are designated for train use, and the third is utilized as a service tunnel. 3 times higher than anticipated, the Channel Tunnel's construction expenditures were approximately $14 million. Nonetheless, the massive undertaking has shown to be well worth the expense, as the Channel Tunnel facilitates annual trade worth over $120 million between the United Kingdom and the rest of Europe. The largest subsea tunnel in terms of total length is the 54-kilometer-long Seikan Tunnel in Japan. However, the Channel Tunnel has the longest underwater section in the world. Following the tragic event of the ferry ship Toya Maru sinking in the Tsugaru Strait during a typhoon in 1954, the tunnel was constructed. Regretfully, more than 1,150 persons lost their lives. Because of the harsh weather, engineers deemed bridge work too dangerous and ferry rides no longer safe. In the end, the government chose to construct a rail tunnel beneath the Tsugaru Strait. In 1971, work on a pilot tunnel got underway. About a dozen years after the excavations began on both sides, they converged in the center. 5 more years later, explosives were used to burst through the seafloor to finish construction on the main tunnel. The Seikan Tunnel, which was built for about $7 billion in all, is still regarded as one of the most amazing feats of engineering. Please remember to subscribe to Facts for Real videos and like this video if you have appreciated it thus far. How do you feel? Which of the earlier projects is the hardest to complete? Tell us in the comments section below. We examine underwater bridges last. Bridges aren't typically thought of as underwater structures, unlike tunnels, yet a significant portion of a bridge's pier may be submerged. Modern deep-water crossing piers can be constructed in a variety of ways. The most widely used methods include driven piles, cofferdams, and caissons. Constructed on land, caissons are made of concrete and are submerged in water, keeping the inside dry. Until the caisson reaches the bedrock and is filled with concrete, the workers continue to excavate sand while keeping the water out. In the end, the caisson serves as the basis for building above water. Large pits with walls and water surrounding them are called cofferdams. A cofferdam creates a safe zone by pumping out the water. The cofferdams are lifted and regular construction continues once the foundations are above water. One of the best techniques for building underwater bridges is to use driven pile foundations. A massive steel column that is machine-driven into the rock is called a driven pile. The entire procedure is comparable to driving a nail into a surface. Concrete is poured into the steel columns after they are in position, giving the bridge a sturdy base. The longest bridge in Bangladesh, measuring 6.15 kilometers, was just finished thanks to the use of driven piles technology. What's even more amazing is that the Padma Bridge is the world's deepest bridge. The steel piles were driven into the riverbed at a record-breaking depth of 127 meters. The fast-moving water created additional difficulties for the Padma Bridge's construction. It complicated the piling process, requiring at least 14 of the bridge's pillars to have their designs altered multiple times over the course of a year. For the engineers, there was also the possibility that in the next century, the soil of the Padma riverbed would shift upward by 65 meters. The construction of the Padma Bridge, which cost $3.8 billion in total, is expected to raise the nation's GDP by 1.2% annually. Some of the economic advantages are already evident because the bridge has decreased travel times by more than 50% and shortened the distance between the industrial center of Khulna and the capital city of Dhaka by more than 100 kilometers. Which one of them was the hardest to assemble? What additional building projects in the ocean come to mind that we ought to discuss? In the comments section below, tell us. We appreciate your time, and we hope to see you in the future video.